This is Darasa Online. Welcome, my dear students, in our physics discussion. In our today's topic is vibrations and waves, but our subtopic is polarization of waves. And if you remember in the previous discussions about the waves, we discussed about the interference of waves, and we saw the interference as done by Young's double experiment, air wedge, and the Newton's ring experiment. We explained the different formulas which are used when solving these two kind of experiments as used. But today, we want to see another important part of the wave, which is called polarization. And in this part of polarization, we're going to look at what the difference between transverse and longitudinal waves before we start our topic, which I see what are the difference between the two waves. Then from there, we can be able now to define what do you mean by polarization. And then we shall discuss the terms which are used in polarization. Now, when talk of transverse waves and longitudinal waves, we can see that transverse these are the types of waves whose vibrations of the particles are perpendicular to the vibration of the waves. So when talk of the waves, we have two aspects. We have the wave itself, which is propagating, and we have the particle. So when talk of the source here, maybe this is the point, starting from here, we can have the waves moving like this. From the point here. These are the maximum points. We call this A, B, C, D. And if you remember this point, these are the crest and troughs. When the wave is moving like that, so the waves is moving, this is the direction of the wave in which it flows. But the particles, they are moving up and down. So can you see the direction of the particles are moving up and down, up and down, up and down. So if you find the direction of the particles here, the ways they move, and you can see how the waves propagate. This is the propagation of the waves. These are the particles. You can see that the wave and the particles are always at the right angle. So you say any kind of wave in which the waves propagate like that is given the name transverse, transversing. So the vibration of the particles are perpendicular or at making right angles to the propagation of the wave. Of course, you remember, example of these light waves, which consist of the electromagnetic waves, which you talk of the magnetic and electric vibrations, which makes this to be as the transverse. In this light, we have the variation of electric and magnetic, which now producing the kind of the waves we're talking about. Light is produced in this form of vibrations of the particles are making 90 degrees with the way the waves move. This is what we call transverse. But longitudinal, this is the waves in which the vibrations of the particles, they are in the same. They means they are along the propagation of the waves. Longitude, they are along. The vibration of the particles are in the same direction of the propagation of the waves. So you can see this, if the waves are moving like that, find a spring which is moving like that. So the waves, you may have a spring which is attached here, spring. And when you stretch it, you can see, I'm talking of horizontal, the particles are moving horizontal, but this you can see the direction here. So when talk of, for example, water surface waves, and then when you are at the end of this water, you push one side of the water surface, you can see the waves are moving like that. They'll be moving, extending there. When they are moving there, they are making waves like that. But you can see how the wave moving. The waves are moving to the other directions, but the particles are moving horizontal. But when you drop an object, you can see that kind of transverse. So the way the particles in longitudinal waves are moving, they are moving in horizontal as the same as the waves move. Can be either in vertical. So they are moving, for example, sound waves. When you speak, the waves are moving to and fro. And as a result, the sound propagates the other side. So the direction of the particles is in the same direction of the propagation of the wave. Now, this is what you can see as the features that distinguish between transverse and longitudinal waves. But we have other factors that we discuss. But our today's discussion will be based on the definition of these, how longitudinal and transverse waves are produced. Now, from these two definitions, you can see that, for example, when you have this is the kind of opening. It's a door. A door. And we have a rope. I have a rope, which is like that. That is going vertical. Sometimes the waves can be passing here. But if you change the orientation of the door, or you change the vibration of the waves, it means this kind of vibration will be blocked. So if you have the waves moving up, down like that, and they maybe going to the door or any kind of opening, sometimes they can be allowed to pass. But when they are moving like that, if you change the orientation of the door, maybe it's changed like that, or if you change the direction of vibrations like that, there is a point now you see that the waves will be blocked. For example, in this case, if the waves are moving up and down like that, and they're passing through the window or the door, which is of the same size, maybe the distance from the top and this will be the same. And if you change the orientation, but maintaining the same distance, you find that these waves will not be allowed to pass. So it depends how the transverse waves are passing through the kind of opening. Sometimes they can pass, sometimes they will not be allowed to pass. For example, let's talk about the longitudinal waves. When you have kind of opening, because they are moving like that, they will be allowed to pass. Even if we change the orientation of the door, they will be allowed to pass. They won't be blocked. So it's very difficult to restrict longitudinal waves because the way they are moving along the way the waves are propagating, the particles. The way particle propagates is very difficult to block. But here in transverse, you have seen that depending the nature of the size of the opening, depending the size, the nature of the openings, maybe it's the window or it's the door, if they are moving like that or vertical, there's a possibility the two waves to be waves. Either they'll be allowed or not allowed. So that's what we talk about, the polarization. Polarization is the process whereby the waves are restricted in a particular direction. The waves are restricted. For example, if you want to allow only a kind of a vertical vibration to pass, you restrict the horizontal vibrations. So if you want to allow the vertical vibration not to pass, so that you can have the horizontal vibrations. So that means that's what we call polarization. And we talk of polarization, we talk of polarization of transverse waves. Now, when we talk of now, you can define polarization as the process of restricting the vibrations of the waves in a particular direction. That process is what we call polarization. And in this talk of polarization, we have terminology that you should know. If you remember, we discussed about this before. The terms that should be known here. One is the unpolarized lights or waves. Polarized. And polarized. And then we have the plane of polarization. Polarization or Z. So now we have British and American language. Now when we talk of unpolarized light, is the waves. Is the wave which has the multiple vibrations. Maybe it's this kind of vibration here. You have the waves, the particles. We have vibrations in vertical, horizontal, as we discussed in the light waves. You can have either vertical and horizontal. All those kind of vibrations can be produced here. But sometimes, if you remember, when you have the bulb is the direction of the waves, the light is in all direction. So it is of this kind of unpolarized light. But the symbol for unpolarized light, we normally resolve this into two components. So one component is vertical, and another component is horizontal. So this is the sign which is used to describe unpolarized light, that it has two components, vertical and horizontal components. But the other component has been resolved into this and the others in the vertical. And in other words, unpolarized light is that which has not restricted in any orientation. But polarized is the one which has been restricted in a particular direction. Maybe it's supposed to be moving vertical or horizontal. The plane of polarization is the plane in which the polarized light is confined. Now look, let's talk about if this is our window, so, or the door, where the waves are passing. Which kind of wave is passing here? This is the vertical, or the vertical vibrations allowed to pass. So you check. Now, if you observe the way those waves are moving, as if they are making them floating and what? On a surface, on a certain plane. When they're moving horizontal like that, it means they're floating on a horizontal plane. Here, they are supposed to be moving in a vertical plane. So the plane where you can see them is given the name the plane of polarization, the plane where those waves seems to be found. That's the meaning of a plane of polarization. I think now you know what do we mean by terms polarization as the process, phenomena of restricting the vibration of the waves in a particular direction. If you want to allow any kind of vibrations, yes. And the point now here is which kind of vibrations is allowed to pass. From this example here, you can see if you draw our axis, this axis of the door is vertical. And the waves, how are they moving? They are moving vertically. So it means vertical, the waves which are vertical, or which are parallel to the opening will be able to pass. If the door is open, and like that, we have in the this is our axis, and we allow to pass the horizontal vibration like that. So if you draw the line, this is our vertical, so the waves are coming like that. These waves will not be allowed because the vertical, and you can see the horizontal, they're making 90. So the waves which are allowed to pass are the ones whose vibrations is parallel to the axis. This is our axis in which the waves can pass. So this axis is given the name as the axis of transmission. Transmission axis. So this is the terminology that we normally use here, the transmission axis. This is the axis which now we talk of the axis of the opening, or something which is allowed light to pass. For this case now, the door, this axis which is vertical, is given the name transmission axis. So if you bring a wave whose vibration is vertical, that means this, if you draw the line in which they are making a vertical axis, so the two axes are parallel. So the principle that these waves whose vibration are vertical will be able to pass. If you bring in a wave whose vibration is horizontal, they will not be allowed. As you have seen, they will be blocked. So we are comfortable now to define the term polarization. Now we have the methods which are normally used to produce polarized light. We have the polarites. We have methods by reflection. We can use by double refraction, by scattering. But our today's discussion will be based on the two highlighted methods, polarites and by reflection. Now, when we talk of polarites, these are special. These are special crystalline materials which has the tendency of polaroids. They have a tendency of absorbing one component of the light, of the waves, and allowing the other component to pass. So the polaroid use the principle of the door, as I said. So the symbol for a polaroid is this. So this, as I said, this is a special crystalline materials which are called sometimes filters. They have a tendency of filtering some of the components and allowing the other component to pass. So here we have the axis. This is the transmission axis. Transmission axis, as I mentioned before. So we have, this is the polarized and unpolarized light. As I said, this is unpolarized. The light which has multiple vibrations. This is the polarized, which has a tendency of what? Absorbing the component which is perpendicular, as we said before. The same principle is applied. The component that will be allowed is the component which is parallel. And you see here, this component will be allowed to pass, and this component, because it's perpendicular to the axis, it's going to be allowed to pass. So the light, after being produced, so the intensity of light here is I naught. This is the intensity of the unpolarized light, intensity of light. After being allowed to pass here, one component has been absorbed, blocked. So the remaining component, it will be vertical, this component here. We normally draw that line, that dot, to show that one of the components has been chopped off. Now, the intensity of light, because we talk of now, it is this vertical plus horizontal. One component is a half. Half of the component has been blocked. So the remaining component is that, half. In mathematics, this is half, because we resolved all the components into vertical and horizontal. So the intensity of the light decreases. That's the principle of the polarization. So the aim of polarization is to reduce the intensity of light. And you can see from here, the component which has been absorbed is the one whose axis is perpendicular to the transmission axis. That is the principle of the polarized. So if you have another polarized arranged here, maybe the second polarized, the name will change. This will be given the name polarizer. Polarizer. Polarized is used to allow some of the light will be able to pass here. And then this will be polarized. And then the name of the polarized, which is now given the name polarizer, is checking whether the light produced by the first polarized, whether it has been polarized or not. So that's the meaning of polarizer. Sometimes it's used to check whether the light produced is being completely polarized. And sometimes the other terminology you should know, when you have the two polarized like that, this is the first axis and another axis here, so that the axes are at right angles. So the two axes are said to be making 90 degrees. So these two polarized are given the name the crossed polarized. Crossed polarized means the axes, they cross each other, and it makes 90. So the crossed polarized, these are the polarized whose axis of transmission is at right angles. So the principle of the polarized is that we have the unpolarized light. That unpolarized light is allowed to pass through the polarized. We have seen that some of the components will be absorbed or blocked, and the component which will be allowed to pass is the one whose axis of vibration is parallel to the transmission axis. And the one will be blocked is the one whose vibrations is perpendicular to the transmission axis. Okay, that's the principle of the polarized. And where do you see this kind of polarized? You can see this polarized in most of the sunglasses. Used to wear sunglasses, reduce the intensity of light entering in your eyes. This is the principle which is normally used to most of the students, that you have this kind of sunglasses and you're enjoying them, but this is the principle of polarization, which is used to reduce the intensity of light so that we can see clearly. Now, the second method is by reflection. By reflection, what do you mean by reflection? It means you can produce polarized light. The light which has been produced is given the name polarized waves or polarized light. Now, how do we produce polarized light? We have the method which I use it to produce. The first one is polarized. Second, by reflection. And you can have other two, which I think we did them when you are in the classes, but I think today is better we focus on these two. Let's see by reflection. What do you mean by reflection? How do you produce polarized light by reflection? Think about the surface. Surface can be a water surface, a plane surface, as we have discussed before, a glass material. That if you draw the normal, that line which makes 90 degrees, it's given a name normal. And the incident ray that is the incident ray is coming here. That incident ray is maybe it is unpolarized light. Unpolarized. This is an experiment which has been done by scientists those years. They passed unpolarized light through a material. And you know from the principle of the reflection, some of the light will be reflected. This is the angle of incidence. This angle are equal according to the law of reflection. The angle of incidence and the angle of reflection are equal. And from there, some of the light will be reflected. That is the angle of reflection. So this is the transmitted ray. Transmitted ray, and this is the incident ray. This is the reflected ray. And we know it can be a surface, grass, water, any material. From the principle what we have, some of the light will be reflected back. When they are reflected back, they must obey the principle of reflection. So the angle of incidence must be equal to the angle of reflection. And some of the light will be reflected, passing through the medium, and it will now make that angle is given as the angle of refraction. Now, here we use Snell's law. When we have the refractive index of materials, we know that this is the material A, maybe is from air to grass. So we talk of refractive index of grass respective to air, which is given by sine of the angle of incidence over sine of the angle of refraction. This is what we have since in the O levels. We know how to find. Now this, because the medium is involved here is air, we talk of the refractive index of grass. So this will be refractive index of grass. So from there, you can be able to deduce the formula which shows now what happened when you increase the angle of incidence, what happened to the angle of reflection and the angle to the angle of refraction. Now let's see how do you combine the reflection and the refraction laws when you are looking about this kind of polarization. For example, it has been found that when this angle of incidence increases, it reaches a point such that this angle is given this I. It reaches a point where the reflected and reflected rays are making 90 degrees. If you remember that when you're increasing the angle of incidence, you're making also this angle to increase and also this to vary. So that, and the observation is so that if you observe the light from here, the observation when it has been done, when you observe the light from the reflected one, it means this beam, most of the light has been polarized. Polarized means the vibrations are in one direction. So, in other words, polarization, or you can produce polarization, particularly by using reflection. That's the meaning of you produce polarization by reflection. Observing the light which has been reflected from the surface, it has been found that most of the light has been polarized. Now, what does it mean here? When you have talk about the refractive index here, if it's the medium here is known, is air. If it's not known, maybe medium 1 to medium 2, we talk of the refractive index here, maybe sine of this angle, refractive index of medium 1, sine of the angle of incidence. This equals to the refractive index of medium 2, sine of the angle of refraction. If this angle is, if this N1 is air, we know the refractive index of air is 1. So you have sine I equals to N2 sine R, and that's where you find that sine I of sine R holds when you have the air involved is the air. The medium involved is air. When the medium is involved is not air, so you're supposed to consider the first medium where the light comes. So from here, we are told when the the reflected beam is completely polarized. That's why you can be able now to reduce the formulas which is involving this. And we shall see this when you are coming to the other examples. But the concept here, you just know in the principle of reflection and the principle of reflection, you can be able now to find the general formula which involves in polarization. Let's go to example 1. Example 1, the question says about a student carrying an experiment using two polarities. And the two waves, A and B. As I mentioned before, you have the first polarity and the second polarity. The name are changing depending the uses of these two polarities. After passing the two waves, A and B, one after the other, through the two polarities, in which the axes of transmissions are parallel. That means the axis of transmission, one polarity is here. This is our first polarity. This is the second polarity. This is first, this is the second. And the transmission axes are parallel. This is an experiment. And a student did that experiment. He observed that the intensity of light from A is reduced. Okay, we have source A and the source A, source B. We don't know the nature of these two waves. But the waves, the intensity from B remain constant. The question is, what was the type of waves from A and B? So those are competency-based. You cannot be given a question straight. So you think about that. We have two waves, A and B. When you pass through this, some of the waves, the intensity decreases. Some of the waves, the intensity is not changing. What do we mean? If you remember, we said we have longitudinal and transverse. The transverse, if you have this kind of vibrations, these are the transverse, the vibration can be affected. So the type A, when this is type A, is passing here, and the intensity is I naught. If it happened, the intensity to be, one of the components to be blocked, it means the intensity of the light will be reduced to half. So after passing here, maybe because we use that. And then we are observing here at the end, maybe because one of the components has been, and the axis is vertical, it will be the same as that. When you pass that, when you observe from that side, you see the waves. This is the polarized light, but the intensity of the light has been produced, has been reduced. But the second part, the second wave, when it is passing here through these two polarities, the intensity remain I, remain I, remain I. If you remember, that is the wave which are given the name longitudinal waves. The orientation of the slit of the opening does not change anything. So from here you can see that from this question, the intensity of light from A has been reduced. So this A must be a transverse wave, because this is the one in which the vibration of the particles can be affected depending the axis of transmission of the polarity. And that B is longitudinal waves. And you should know the reason. We have seen before how these two waves are supposed to be distinguished. Part B, explain what happened to wave A after passing through the polarity. After passing through the first polarity, it means the component of the A, which is a transverse, which is parallel to the axis of transmissions, will be allowed. But the component of the waves, which is perpendicular to the axis of transmission, will be blocked. That's why you can see one of the components has been absorbed here, and it remains half of two. But here, again, the axis of transmission is parallel to that, so that component will be allowed to pass. That is the reason why the intensity of the light reduces. C, what happens to the intensity of the waves from A when the second polarity is rotated until the axes are at right angles? Okay, very interesting. Assuming that after passing through the first polarity here, that was A naught. from this unpolarized light through this parallel here. The axis is this axis. Which component will be allowed to pass is only this vertical. So we have this component here, which will be allowed to pass. So this is the polarized light, polarized, and the intensity reduced to half of the original. Then, what happened when the second point now is rotated until the axis here, they are at right angles. The two is making 90. So it means here, and you can see, when you pass here, this component here is, which is left, is vertical, and the axis of transmission is horizontal. If you observe from this side, you can see that the intensity reduces to 0. Why? Because the transmission axis and the vibration of the particle of the waves are at right angles. So the intensity of the wave reduces to 0. Very interesting. That's how you can use the concept of polarization in answering those questions. Example number 2. Example number 2 about the polarization. The question says, A, we have a parallel beam of light which is incident on the surface of the transparent medium of refractive index n. And sometimes you use n or use n as symbols, that the angle of incidence is given I. If the reflected and the refracted beams are at right angles to each other, assuming the law of reflection and refraction holds, determine the relationship between n and I. We did it before. Very quickly, you can see this is the information we have, that this is the angle of incidence increases such that this is the angle, and this is the reflected, and this is the refracted, and this is the 90 degrees. We call this now, remember, this now is completely polarized. And what is 90 here? This angle is I, also from the law of reflection, as the question says. Assuming the law of reflection holds, and the reflection now means what this R. So if this is from air, it now going to the second medium is air, to the second medium, which is N. So from here you have refractive index equals to sine I over sine R. That is from the law of the refraction. But I plus R, what is I plus R? This angle here. This is 90. This on the whole of this, because the straight line is 180, so I plus R should be 90, so that when you add this 90, you get 180. So you make R a subject. From here is 90 minus I. If you substitute in the formula, you have N equals to sine I over sine R, which is 90 minus I. In mathematics, this is I sine I over cos I, which is tan of the angle I. Okay, that is how the N and I are related, and sometimes this is what we call Bristol's law. And this I is the angle of polarization, or Bristol's angle. Bristol's angle, if you remember. So the question is asking to find the relationship between N and I. So that is the N equals the tan of the angle of incidence. Part B. A beam of light traveling in water strikes a glass plate which is also immersed in water. If the angle of incidence is 51 degrees and the reflected beam is found to be completely polarized, find the refractive index of a glass, given that refractive index of water is 1.3. The same concept here. We had before it was air. Now here it is now strikes the glass and going to water, is immersed now in water. So here we have the medium. Here we have two medium. A beam of light is traveling in water, strikes a glass which is immersed in liquid. So you have water. So you have water. So it's from water to the glass. And the medium here, we have refractive index of water, and we have the refractive index of glass supposed to be found. So from this we find that it is N1 sine I equals to N2 sine R. What is I? I is the angle of incidence, which is given. I is given as 51. And you know R. R is 90. R equals to 90. Of course, you remember how R is rated from this question. R is 90 minus that, which you get 39. So we have N1 sine 51 equals to N2. That N1 is the refractive index of water, which is given 1.3. This is N2, refractive index of glass, supposed to be found. Now, this is sine of 39. What is N2? N2 equals to 1.3 times sine of 51 divided by sine of 39. In other words, if you convert this sine of 39 to be sine of 90 minus that, which is the same as 1.5, sorry, same as 1.5, N2 equals to 1.5 times sine 51 over sine 90 minus 51. Of course, you said this is the same as 1 times the sine 51 over cos 51, which is 1.5 tan of 51, which is now easy to find. You find what is tan of 51 from there, from a calculator of 51. And then multiply by 1.5. This is 1.23. Multiply by 1.5, get multiply by, what is that? 1.5, 1.3 means effective index of water is 1.3, not 1.5. 1.3, 1.3, 1.3 times 1.3. 1.3 times tan of 51, which gives us 1.6. That is the refractive index of glass, depending on the nature of the glass you have. Okay, that's how you can solve different questions involving the concept of Bristol's law, which has been found from the concept of polarization. Now, as an assignment, we have a beam of unpolarized light, which is incident on at an angle of 80 degrees on a plane surface, such that the reflected beam is completely polarized. So, the question is asking to find what is the refractive index of glass. B, calculate the angle of refraction of the transmitted beam. So this is the question for you, everywhere you are watching. Now let's do this together. Take your calculator and see how do you go about this. So the question is given at the angle. This angle of incidence is given. I is 58, the angle of incidence. This is the question. The beam unpolarized light is falling on the surface here. And that angle of incidence, sometimes we call the angle of polarization or polarizing angle. And it makes the beam which has been reflected here to be plane polarized. So this is 90 degrees. And from there, we are supposed to use the formula for tan of that angle. So we know the angle of incidence is given from this question. And because it's given that it is falling on the surface of the plane, we assume that is from air, from the air surface. That's why we can take this as air or as glass. But if the question is given that it's coming from another medium, that means the effective index of the first medium should be introduced. Since we are not given any information about the second medium, maybe we assume that this medium was air. The light was from air. And here, we are talking about the refractive index of glass, which is the asking there. So our refractive index of glass equals to the tan of that angle of incidence. So using your calculator, you can find that value, tan of 58, which is 1.6 again. 1.6. So that's how you can be given a question in different way. So now you can see that we have found the value of refractive index of glass, since the angle of incidence was given as 58 degrees, but the information we've found here is that the reflected beam is completely polarized. We know from the principle of polarization, when this polarized light is completely polarized, it means the angle between the reflected and the refracted should be at the right angles, 90 degrees. And from there, you're supposed to apply the Bristol's theorem, the question. From there, you can apply the concept of this polarization to get the values 1.6. But mind you, if the question is not talking about air, you should know you're supposed to start from N1. N1, sine of the angle of incidence in the first medium, equals N2, which means the refractive index of the second medium times the angle of refraction in the second medium. But here, since in the first medium, our air is the medium, which means the refractive index of air is 1. And we have used that to get 1.6. B, what will be the angle of refraction of the transmitted beam? The angle of refraction is given. We remember that the reflected and refracted beam at right angles. So the principle, you know, from the principle of the polarization by reflection, is that when this observation is shown from here, that means this is completely polarized. And it makes the 90 degrees with this. And if this is 90, we saw that that is I, the angle of incidence, plus the angle of this R. This is the angle now of polarization, which is given as 58. We get 90 degrees. So our R equals to 90 degrees minus I. What is our angle of incidence? 58. So 90 minus 58 R equals to 32 degrees. So that is the angle of refraction of the transmitted beam in the second medium. So far, we have seen the importance of polarization in our life. And we have seen some of the questions that may be given based on the competence-based system. And that means you are aware and you are comfortable now on how to use the formulas given, especially in this Bristol theorem, when explaining how do we find the angle of incidence, how do we find the angle of refraction, how do we find the refractive index of materials. And also, we have seen how do we use polaroids to produce polarized light. And we mentioned some areas where this kind of polarization can be applied. So to mention a few, we said this polarization concept is not that we are making in class, but it has a lot of applications in your life. We said before, but it can be also applied in engineering, in industries, and sometimes in medicine. So in industry, sometimes this concept of polarized light is used to determine the fractures of metals. When the light is passed through, in some engineering works, some railroad tracks like this, it's not easy to know where is the fracture here, but they send this kind of polarized light so can be able to detect this kind of fractures. Also, in music, they normally used to view the pictures in all dimensions. So we have the light cameras. We have two cameras which are set. One camera is taking a picture from one side. It means your eyes will be focusing on the right-hand side. Your left eyes will be observing the image from that side. And your eyes from the right will be observing the image from the left-hand side. And as a result, you're going to be able to have the good view of the pictures produced because of that. So that's very interesting on how you can use polarizations in making movies, observing movies and pictures which are supposed to be observed in high quality. So those are few applications of polarized light. But in the second period, which is becoming part 2 of this polarization, we're going to see now what happens when the polarities are not parallel like this. With the polarities, we said and these two polarities are said to be parallel. The axis of transformation is parallel or is perpendicular. What happened when this one of the polarities is making a certain angle, which is not 90 or here, is making an angle, maybe this is angle theta. It's not 0. When they're parallel, means the angle is 0. When they're perpendicular, means the angle is 90. Now, what happened when this angle here in between is 30, is 10, is 20? How do you find the intensity of the light emitted from the two? Very interesting. Keep on watching. We'll be able to see how do we find the intensity of light from here. We know it will be a half. How do we find the intensity when the light is passing through the second polarity, which is inclined at the 30? It's very difficult to find unless we have the concept on how to find these from the second angle, from the second polarity, which is inclined at a certain angle, which is not either 0 or 90. That's where you are supposed to watch the second part of this part of polarization. Keep in touch. Stay at home. Goodbye.